Salutations, everyone. Welcome back. So, up until this point, we've kind of been gathering a bunch of equations. Let's play around with it a little bit, shall we? Let's play around with what we've gotten. So if we look at our acceleration and we cross it with our angular momentum, mu, I'm going to write it this way just because it looks a little bit neater when I do. And let's break it down a bit further before I explain motivations behind anything. All right. So on the surface, it is difficult to see why we want to take that particular cross product, why we want to take R double dot and cross it with H. And truth be told, I've looked at several textbooks, I've looked through my notes, I haven't been able to find anything that explicitly states we want to do this because of this reasoning. So if anybody watching this video happens to know why on the surface we want to do this, please leave a comment and I'll try to read through it, and I may make a follow-up video or I may just pin the comments. But I myself am curious, and I am certain that I am not the only one. As far as I'm able to tell, we use R double dot cross H specifically because then we can turn it into R cross R dot. That's the closest I've gotten to an answer, but alas, we must move on. This quantity right here looks a little fun, shall we say, to deal with, but there is a mathematical property known as the, I skipped a word, let me try this again, known as the vector triple product. I'm actually gonna do that just because it's my system. Blues for notes. So for the vector triple product, I'm not going to spend a huge amount of time on this, but at least enough to sort of demonstrate what's going on. So we have A vector cross B vector cross C vector. And the way I remember this be A dotted with C minus C A dotted with B. Back cab. That's the mnemonic that I have in my mind, and it's been working for me so far. So we'll take that principle and we'll apply it over here. Let's mu over R cubed. We'll put in our bracket. Our B vector is the second R. Our A is the first R vector, and it is dotted with C. I really wrote A vector, hang on. Our A is our R vector, and our C is our R dot vector. There we go. Minus C A net B. And today is not the day either that I shall become better at multitasking. Alas, we move on all the same. So let's combine some terms. R times R dot, well, that's just going to be the magnitudes. That's going to be times the r vector, and we're going to subtract. Well, yeah, we've seen the dot product times itself before, so we know what to do, even though our pen doesn't quite know what to do. Times our dot vector. Let's go down to here. And let's do that. Now we can distribute. So minus mu r dot r vector r cubed minus negative mu r squared r dot vector over r cubed. And we can reduce this mu r dot r vector over r squared. The negative is negated, plus mu r dot vector over r. And once again, that is our acceleration. Come on, there we go. Crossed with our angular momentum. All right. Scroll down a little bit more. This doesn't look like it's quite any better of an equation to deal with, but the mathematically inclined among you may take note that on the left side, on the left-hand side, we just might be able to take the velocity vector crossed with the angular momentum vector. And if we do that, we get the derivative of the first crossed with the second plus the first crossed with the derivative of the second. And having done a huge video already on the angular momentum, we know that that's going to be 0. Any number times 0 is going to be 0, and our angular momentum is a constant of motion, 0. Which then leaves us with our right-hand term. So maybe we can do the same thing to our right-hand side. And sure enough, we do mu r vector over r. I'll start by taking the mu outside. No, I won't. No, I won't, because it'll look neater if I don't. So mu derivative of the first, that is going to be our dot vector over r. And then we add in mu r, and then the derivative of the denominator, which is going to be minus 1 times r dot over r squared. All right, we're going to come up to the final equation here in a minute, or whenever I decide to inject this, really. But I want to take a moment of your time to describe what is happening in this step, namely during that part of the step, because this wasn't something that I was completely aware of when I was recording the first time. What is, I believe I had described it as the radius dotted with the velocity, and I decided to name that r dot. That's actually not what's happening. What is actually happening is our radius is being dotted with dr dt. And I know I just said the same thing again, but actually I did not. What this means actually is that we are looking at the change in radius, which means that we are only ever looking, let me write it down here, we are only ever looking at the radial components. So no tangential components to our velocity, it's just what's happening in the radius. So really here, what I should be writing instead hang on, let me write down. I like my colors. What's actually happening there is we are looking at R V sub R. So, and that becomes a little bit more obvious when you get down to this step. When you think about it, when we get to this portion of the step, we're looking at, oh, the change in the radius, right? Not the velocity, the change in radius, excuse me. So it's a little tricky. Hopefully that clears it up. But rest assured, that is the only mistake I will ever make. And sure enough, that is our right-hand side. So let's rewrite that equation from before using our derivatives here. All right. Now, this looks somewhat better. We have fewer terms, but now we have derivatives here. All right, let's integrate to remove the derivatives. That'll make it easier. Cross with H equals mu R vector over R. And because we are integrating, we must remember a constant of integration. Because it is a vector equation, so too is our constant of integration. All right. What is our constant of integration? Let's solve for that. It's going to be R dot crossed with H minus mu R vector over R. All right. Let's take a moment to look at our units. So we're looking for what unit C is going to have. So for that, let's look at our first term, which is going to be kilometers per second. And it's going to be multiplied by kilometers cubed per second. And that has to be the same unit set as our second term here. So let's put in a comma. Our mu is kilometers cubed. I just realized I misspoke and miswrote. That's supposed to be kilometers squared per second. Excuse me. But our mu is kilometers cubed per second squared. And then it is multiplied by kilometers over kilometers. All right, well, that one goes away. Kilometers times kilometers squared is kilometers cubed. Seconds times second is second squared. All right, sure enough, we have kilometers cubed per second squared, which a way to look at that is the volumetric acceleration. That doesn't seem very nice to work with. So let's go ahead and see about getting rid of that. Well, if we divide by our constant mu here, which is kilometers cubed per second squared, we can turn that into a unitless value. So let's go ahead and do that. C by mu is equal to 1 over mu times R dot crossed with H minus R over R. And scroll down a little bit. I'm going to make a claim here. That is going to be our eccentricity. box that in. That is an important equation to box, after all. And that is our eccentricity. And what's more, that happens to be another constant of motion. So in the interest of proving it, it's dt E equals d dt. And then we didn't really do anything super special in creating C. We integrated that to find a constant of motion, and now we are just going to derive it again. And in fact, instead of trying to prove that this whole thing is zero, we know that it's going to be equal to C over mu. I'm just going to go ahead and use that as a shortcut. E dot is equal to, and now we get to use the quotient rule. Mu, C dot minus C mu dot over mu squared. Well, C is literally a constant of integration. Mu is the gravitational parameter of Earth. I sincerely hope that that does not change, which sounds to me like 0 minus 0, making that a zero vector. Well, that was fairly painless. I'll tell you what. Let's make that look neater so that we all know what I'm talking about later on. All right. And there you have it. Not only our eccentricity equation, but also a proof that it is indeed a constant of motion. Now, I think there's going to be enough time for an example. And if you will excuse me, I'm going to fill in everything really quick, and then I will be right back. All right. This is going to be our starting information. So we have, and I'll mark it in red, why not? We have our radius and our velocity vectors as they have been presented to us throughout the whole series so far. We also have our specific angular momentum, which we know what that is because we've solved for that before in a previous episode. And that just comes about because of R and R dot. And then we also have our gravitational parameter for Earth. That should be all the information that we really need in order to start with this equation. Let's see, what did I... dot H divided by mu minus R over R. All right. So let's start with R dot cross H. Let's go ahead and write that in. You are a hat. Velocity, radial direction. Angular momentum in the radial direction. Velocity in the tangential direction. I realized I copied this down wrong. That's supposed to be it. That is supposed to be a 5. 0.3455. Angular momentum tangential is going to be 0, of course. And then UZ. 0 velocity in that direction. 87,481 in the Z direction, which will then turn into, and I'm going to write it in as a vector, just kind of going past the intermediate step. So we have 2 non-zero numbers minus a 0. 4, 6, 7, 6, 2, 9.6855. All right. And then our next term, because that is the second entry in the cross product, is negated. That's going to be these 2 non-zero numbers multiplied together, and these 2 zero numbers multiplied together. It's going to be 39,856.3436. And then this term is 0 because we have 2 numbers. Well, we have a non-zero multiplied by 0 and a non-zero multiplied by 0. Surprise, surprise, that turns into a 0. Okay. Then we're going to divide it by mu. And I'm actually going to write it over here. So we'll take this first value divided by mu first. We're going to get a number that is 1.17310. Whoop. No, we're not. 1.80345. And our second number is 0.099990827, and then dividing 0 by that number. Cool. And our second one, our second term here, r vector over r, that is the normalized radius. And since radius only has the r component, 1, 0, 0. So cleaning that up, we are going to get, actually, just because I'm at the bottom of my sketch pad down here, I'm going to scroll down a little bit. So now we have 0.173180345. Second term remains unchanged. And our third term is 0 minus 0. That is our eccentricity vector. But while we're here, I think we got a little bit of time left. While we're here, let's also take a look at the scalar of eccentricity, which is just going to be the square root of e sub r squared plus e sub theta squared plus e sub z squared. And I'm writing it out like that because I don't want to have to write all of these digits again if I don't have to. And if we're willing to round it, 0.2. Make that 2 look a little bit nicer. There we go. Not 0.2. It's almost as if I've picked that number specifically. All right, so we have eccentricity. Why do we care about eccentricity? I'm glad you asked. You're so inquisitive. I like that. So in the previous episode, I believe it was, we talked about the specific orbital energy and how when the energy was less than 0, we had a closed orbit, a circle or an ellipse. And then if it was greater than 0, we had an open orbit where the satellite just kind of runs away from its host body and is never seen again, barring outside forces. That is more of a consequence than a definition. The definition of our orbit types are going to be based off of eccentricity here. So if E is equal to 0, that is defined as a circular orbit. If 0 is less than E is less than 1, if E is between 0 and 1, that is defined as an elliptical orbit. If E is equal to 1, that is going to be defined as a parabolic orbit. And really, I shouldn't use the word orbit. It's the parabolic trajectory. And then for all E's that are greater than 1, those are hyperbolic. They are hyperbolic trajectories. And we're going to explore them a little bit more throughout the series. For the short term, we are going to look at closed orbits because there are still a few definitions yet to be derived. But to give you something to look forward to, we will be looking at trajectories and escapes from orbit. So we're calling these eccentricities, and we're describing our orbits and trajectories as circular, elliptical, parabolic, hyperbolic. These are all conic sections, which we'll be getting into that later. But because of that, we can use all sorts of definitions and tricks for ellipses to help us figure out other properties of our orbit. And we're going to be taking a look at that later on. But I think that's a good enough place to end this episode. So thank you so much for stopping by. I hope you have a wonderful rest of your day.